Today we're going on to look at series and parallel circuits, our third lesson for electrical circuits. And this is where we start to draw together knowledge from the previous two. So we're going to start by looking at series circuits because they're the simplest ones and we need to know how current and voltage behave in those. And then we're going to keep those rules when we look at the more complex parallel circuits. So to start with, our two rules, fairly straightforward. The first thing you need to know is that current must be conserved. So whenever you're looking at a circuit, whatever the current is at the beginning, that must be maintained. If you start with 6 amps, by the end of the circuit, there should be still 6 amps in that circuit. And voltage, for voltage, you need to look at individual electrons, and every electron must use up its voltage. If they carry any voltage or any potential back to the battery will heat up and explode. Okay, so those are our two simple rules that we have to maintain in every single circuit we look at. Let's start with then series circuit. Series circuit is when all the components are on a single loop. So you can see in this diagram, start with a 3-cell battery at the top, then we have a closed switch, followed by a lamp or a bulb, another lamp, and then a thermistor. So you should be able to identify these from what you learned in lesson 2. It's also useful to be able to come up with an example of where this might be used. So this would be any time you've got a circuit where the temperature would be affecting whether the lights are on. So you might see this on something like an iron, where the light either comes on or goes off when it reaches the required temperature, that sort of thing. Right, so this would be a series circuit because everything is on a single loop. There are no junctions in this circuit, and that is what we use to identify when things are in series, that there's no junctions between things. We're looking at how current behaves in a series circuit, so we're applying our first rule that current must be conserved. So series circuits are pretty straightforward. So we've got our battery at the top, 3 amps being pushed around by this battery. Doesn't matter about their voltage at this point because we need to think about them separately. And in order to conserve them, if there's no way for that current to go off, there must still be 3 amps at the next arrowhead. And generally speaking, the WJC use arrowheads to indicate where they want current to be labelled. Okay, so again, there's no option for any of the current to leave between this arrowhead and the next. So we've still got 3 amps, still nowhere for it to go. So all of our arrowheads should be labelled the same amount. Okay, and that is how a series circuit works. So one of the additional rules is that current is the same at every point. And that only applies in a series circuit. Moving on to voltage, so this is rule 2. So when we're looking at voltage, we need to consider what's happening to a single electron. So all of the electrons leaving the battery will be ladened up with the voltage of the battery. So we've got a 6-volt battery, so this individual electron is carrying 6 volts. Okay, and it must use up that 6 volts by the time it gets all the way around to the other side of the battery. So by the time that electron reaches here, it must be at 0 volts. So somewhere on that loop, it's got to use up those 6 volts. Now, you would be given additional information in a question to help you with something like this. Okay, but the 6 volts have got to be used up in the lamp and in the resistor. And because neither are labelled, it doesn't matter how you label it as long as these two consume the 6 volts. So I'm going to say that the lamp is going to get 2 volts and the resistor is going to get 4 volts. Okay, so as the electron enters this point, it's at 6 volts. The lamp steals 2, so at this point, it's got 4 volts. So it goes around into the resistor with 4 volts. So by the time it leaves the resistor, that electron is then at 0 volts, which means it's got no potential left, so it can go back to the battery. So looking at some worked examples for this, I would strongly recommend that you separate the two things, current and voltage, and deal with them separately. So dealing with the current first, we need to think about all of the electrons collectively. So we've got 1.5 amps, however many electrons that is. And then because there's no way for those electrons to go off elsewhere, we must still have 1.5 amps there. Following the series circuit round, no way for the current to leave, 1.5 amps, and that'll be the same all the way around. Okay, and because none of it is left, we had 1.5 amps leaving, 1.5 amps returning, so therefore we have applied rule 1 where the current must be conserved. Then separately thinking about the voltage, we're going to think about what's happening to that individual electron. So one electron leaving the battery will start off with 12 volts. And by the time it gets back, it's going to have 0 volts. So around this loop, it needs to find places to get rid of those 12 volts. Now, to keep this simple, I'm going to say that these bulbs were all identical. So they should receive the same amount of voltage each, 3 volts each. And in doing so, that use of voltage as the electron moves around adds up with 3, 6, 9, 12 volts. So all of its voltage has been used. So by the time it leaves this last bulb, it's got no voltage left, so it can go back to the battery without causing problems. What's more likely in a WJC question is that they'll give you some additional values for the voltages of the other components, and you just need to make sure that you're applying the rule to make sure that the voltages balance. So on this one, exactly the same circuit, but I've labelled up a couple of the batteries. So remember, the electron leaving the battery has 12 volts. It's going to use 3 volts up in the second, 4 volts up in the third, and 1 volt up in the last one. So these 3 bulbs collectively will consume 8 of the volts. That means that this one, in order to get rid of all 12, must consume 4 volts. So we've got 4 plus 3 plus 4 plus 1 gives us a total of 12 volts being used up around the circuit. Okay. Now, obviously, it's not always going to be 12 volts. It completely depends on what the battery is labelled as, but we need to make sure that the total consumption of potential around the circuit matches the voltage of the battery. So on your assignment, there will be a worksheet for you to try these, all based on series circuits, because they're the most straightforward and they'll be easier to try before you go on to the more complex parallel circuits.